Okay, as promised, I am going to go ahead and go through each mechanism of the ones in the book. And these were all in the book, and I'm just gonna kind of talk you through them and explain it to you. So let's go ahead and get started. So the first one we talked about was the mechanism for hydrohalogenation. What we said in hydrohalogenation was the double bond is acting as the nucleophile to get to the partially positive side of our acid, and that's going to be the hydrogen. Okay, so in that case here, we have our pi electrons are going to reach out and create a new sigma bond, both of those pi electrons, with the hydrogen, and then the two electrons between the hydrogen and the halogen are going to go onto there, creating our new nucleophile. Notice what we also do is we created a carbocation. Okay, so that was the slow step to generate the carbocation because it has the highest transition energy right here, transition state energy. Now the next step is very fast because we now have a new nucleophile and we already have a positive charge. So these electrons are going to kick in, create a new bond with the carbon, a new sigma bond between the carbon and the halogen. Okay, so that's what our second step here on our energy diagram is. So we generate a carbocation, and then that carbocation is very reactive and reacts with our halogen, which is our new nucleophile. Okay, for hydration, for primaries, it's not that way, but for secondaries and tertiaries, they go through the exact same mechanism. What we have is we have our acid catalyzed water, and so in this case, we form hydronium ion. Okay, the alkene acts as a nucleophile, reaches out and create a new sigma bond with a hydrogen, generating water as a neutral species and a carbocation. And what we know about our SN1 reaction is that once you have a carbocation, even weak nucleophiles can react. So what we have happen is the lone pair from the oxygen is going to come in and attack the carbocation, generating our protonated alcohol. Okay, so now we can have this water act as a base and come in and remove this extra hydrogen here. Those electrons go back down, so we have two lone pairs on our oxygen, and we've regenerated our water, our hydronium ion, from the water, and therefore we can go back and reuse it again. So that's why it's a catalytic hydration, because we get to regenerate the catalyst over and over again. The water itself is not good enough to help it do that, because we would have a nucleophile reacting with the nucleophile. So by having the protonated water, now we can do it where our alkene is the nucleophile and our protonated water is where we find the electrophile. Okay, so now I think this is a little bit different than what I said in class, so this is important here. So in the oxymercurization demercurization step, the first thing we want to do is we have our nucleophile again, but we need to generate our electrophile. So we generate our electrophile by having one of these acetate ions leaving there, and since mercury is +2, it now has a net +1 charge. So now we have a +1 charge, so that's a very good electrophile. And so our nucleophile is going to come and generate a bond with that, again, leaving the more stable bond with a partially positive charge. Note it's trying to associate with it because it's still partially positive. It's still trying to get this secondary bond here. But notice what it does. It means the mercury is staying on the least substituted side, and just like a proton would. And so then we have our partially positive carbon here. Now our water can come in and act as the nucleophile. So in this case, our water can come in and act as the nucleophile and make a new sigma bond. And notice we have a protonated alcohol from that product here. Okay, so what we can do next is use something else in there like water and remove one of these hydrogens, add it to the water to generate acid, which is not required for the reaction, but is a output of the reaction. This pair of electrons becomes the lone pair on the alcohol, and then we're left with our alcohol that did not rearrange because it never formed a full carbocation. Notice there's a partial bond between the mercury and that partial positive bond, so it does not rearrange, but it makes it activated for the water to come in and act as a nucleophile. Now, the next step, of course, is to take this and reduce it off with the sodium borohydride. And we'll get into the hydride mechanism in a little bit, in a different chapter. All right, so now let's look at the hydroboration. Okay, so the hydroboration is the one that gives us a primary. Okay, and there's two real reasons it gives us a primary. One of them is that it has a steric demand. The boron wants to stay on the least hindered side. So when the boron lines up next to our alkene, we have these electrons are going to kick in and transfer the hydride to our carbon, okay, our hydride, because it's taking both electrons. Then we're taking the two electrons from the alkene and making a partial bond with the boron here, and therefore we get cis addition in this transition state. This is our transition state, and we get this syn addition where they add on the same side, and the boron is directed toward the least substituted side because of sterics. Okay, so if we look at that again, remember that boron here has 3 bonds, so it has an empty p orbital right here. So what's happening is we're getting a compound between, we're getting a pre-association with the pi bond and this empty p orbital here, because it only has 6 valence electrons, right? So it gets close to there and starts to get, you know, lining up. And then it moves over for the transition state so that it can move these electrons into here and these electrons, oops, let me change color. Here, let me change to red. And so these electrons right here are going to come up and create a new sigma bond here. Both of the electrons in the pi cloud are going to come down into this orbital and generate our new bond with boron. Now notice, once we do that, we're using an sp3 hybridized carbon orbital, and we're using an sp2 hybridized boron orbital. And so we're getting that nice sigma bond overlap. All right, so this gives you a good idea. Remembering this transition state right here gives you a good idea that it's going to add syn addition, and the boron's always going to be on the least substituted side. All right, now the mechanism for halogenation is really interesting because the bromine-bromine bond is not polar at this time. So what it's doing is it's coming close to the pi cloud of the alkene, and that induces a partially positive charge over here and a partially negative charge. Remember induced dipole interactions where you have them coming together and they decide to polarize their bonds so that they can do this. This is what happens in the case of our bromine here. So we're going to have the 2 electrons from the alkene, which is our nucleophile, reach out and form a bond with the bromine, but the bromine's also going to reach out with its electrons and form a bond with the other carbon. So these 2 electrons are from our bromine, and these 2 electrons are from our alkene. Okay, so now we have this intermediate, and you can actually isolate it, but what's going to happen is it wants to open up because of ring strain. So it really wants to open up. So we're going to have it hit with a nucleophile. In this case, the bromide ion generated when we created that first complex, and it has to come in to the back. So it has to do our anti-addition, because this bromine is covering one side of it. It has to come into the other side of it, giving us our anti-isomer. Now, if it attacks this side, it's going to give this isomer here, which is our vicinal dibromide. But if it attacked over here, it is going to give the enantiomer, okay, depending on what the substitutions are. So that's why we actually have to have the vicinal dibromide plus its enantiomer as the correct answer. All right, so now let's look at the HaloHydrogen reaction. The HaloHydrogen reaction starts exactly the same way as the halogenation does. We have the polarization of the halogen, the bromine and the chlorine, and then it forms the halonium ion here. Now, in the case of a HaloHydrogen reaction, a lot of times you use water as the solvent. So you have so much more water than you have halogen that what's going to happen is that your water can act as the nucleophile and open up the ring and then lose a proton to water again, and giving us our halogen on one side and our alcohol on the other, and generating an equivalent of acid. And so, and then that would be the counter ion to the bromide that's coming up. Okay. And our last one of our ones is we have two ways to do Syndihydroxylation. Syndihydroxylation. So we're going to have a 1,2-diol when we do this. And so the first reaction we have is actually using the osmium tetroxide right here. And then it forms this osmate ester intermediate here. Okay, now that is stable there. That's why we actually have to add the sodium hydrogen sulfide to break this osmium oxygen bond here, reduce it down to give us this osmium dihydroxide compound. And then this is no longer usable. But note, remember, look in the book, we have that thing where you use the NMO, which can re-oxidize this back to osmium tetroxide. So you can use only catalytic amounts. So what we'll see here in all of our systems is we'll have that syn addition across there. So on rings, it'll be on the same side. On our alkenes, we now have free rotation, so we might want to look for where our stereocenters are bent. There's one more reaction that we can actually do with cold potassium permanganate. And it basically has a similar mechanism where it forms the permanganate is going to form this kind of permanganate ester. And then once we add a little water to it, it'll hydrolyze those manganese oxygen bonds and then give us our diol. But note, this has to be cold. What happens if it's hot? We saw that if it's hot, it actually breaks double bonds. Okay, so let's talk about breaking double bonds. And let's first start with the ozone. The ozone is really kind of one of our go-tos because we can have two different ways to work it up. We have a reducing workup and we have an oxidative workup. In the case of this, we're using a reducing workup. Reducing workups include things with dimethyl sulfide or zinc, zinc metal, and it does zinc electron transfers until it becomes zinc +2. Okay, so the first step in the reaction is we actually have this molecule here. Notice it has a permanent or an anion here and a cation here in our system. So we actually have we have an activated system where this positive charge can go back and forth right here through our just moving those electrons, right? So that's why our alkene acting as our nucleophile will come in and bind to this. When it does that, it kicks these electrons on and the anion can come to this positive forming charge on the other side. When it does that, it gives us this nice weird five-membered ring. But then it really doesn't last very long like that, and it fragments. And so the first fragment turns into our ketone right here, and then we have another fragment with this oxygen ion. Now, they don't have that much time to float away from each other. Okay, so what they do is then now we have two reactive species. Again, we have our cation here, which can move from here to here. And so we'll end up having our anion on our oxygen side here attack the carbonyl of the carbon, because there's a partially positive charge there on all carbonyls. That'll kick out these electrons to kick out this to give us our partially positive carbon on this side. And then we'll have our electrons rest on here, giving us neutral. Everything has a zero formal charge. Now, what we're going to do next is we're going to have the sulfur come and take away one of these oxygens. So one of the oxygens is going to stay with one of the carbons. The other oxygen is going to stay with the other carbon, giving us our carbonyl compounds. And remember, we can make aldehydes and ketones if we use this reducing environment. Okay, so that's the key step here, either the zinc or the dimethyl sulfide. Okay, so if we use permanganate hot, when we use permanganate hot, what we're going to end up doing is if you have a hydrogen on either side of this, that side is going to become a carboxylic acid. Because the permanganate is a strong oxidizer, it will just keep oxidizing down until it turns it into a carboxylic acid. However, if there's two carbons on that side, it does stop at the ketone. So in this case here, with this unsymmetrical side, this side right here keeps going down until it becomes carbonic acid, and then carbonic acid breaks down into CO2 and water. So that's a very clean reaction you can get for one of these exomethylene type structures here. It'll give you just one product, which is the important part. So like before, it's a syn addition reaction here. We formed this intermediate with the permanganate ion here. And then what happens is the electrons move from here. These electrons form a double bond. These electrons come down and form a double bond, breaking the carbon-carbon bond. So the fact that we have a ring and we're going to move electrons 1, 2, 3 that's why the carbon-carbon bond breaks and we end up with the two carbonyls or the two carbon-oxygen double bonds. Okay. Now, that would initially form this aldehyde, but unfortunately, in the case of any time you have water and an oxidizer around, it's going to oxidize your aldehydes down to carboxylic acids. But the key note here is it's going to break that carbon-carbon bond where the alkene was. So you want to always try to draw the line right here in the middle of the alkene, saying it's going to break here, and those two carbons are going to have carbon-oxygen double bonds or carbonyls on them. Okay. So when we have halogenation for alkynes, it's exactly like alkenes. We're going to do it first, where we add one hydrogen on it and then the second hydrogen on it, and it'll stop at the haloalkene. Okay. If you add a second equivalent of it, you're going to get the geminal dihalide. Remember, both of the halides are going to be on the same carbon because you have a hydrogen on that carbon, and it's a Markovnikov-based addition, so we're going to put another hydrogen there. So we're going to see it go from this right here, and I'm just going to put CH3 groups here. And we're going to go for one equivalent, and it's going to give us hydrogen and CH3 and a double bond and let's see, it is Markovnikov's. So it's going to give us CH3 and a chlorine. Okay, and then the second equivalent is going to add across here, but the hydrogen is going to add to this side because it's going to be where it's Markovnikov again. So we're going to have a hydrogen here and our chloride here, and we have the single bond, and we have the CH3 and the other chloride that we already had on there, the hydrogen we already had on there, and the CH3. So we have our second equivalent added across, giving us our geminal dihalide. Okay, so at the back of your book, you have this right here, and I hope you're doing your reaction tables. One of the cool things about this one is it kind of lays it out how you would want it to happen, right? This is one of your reagents here. This is the next reagent for hydrohalogenation. This is the reagent for our hydration, okay? But notice that this is where our electrophile is. It's showing you exactly which side is the electrophile and which part is the nucleophile in part of that step. Okay, also it shows you the key intermediates here. So in this right here, it tells you why you get a mixture of syn and anti-addition, because it can go to either side of that carbocation. It tells us your regiochemistry. It tells you stereochemistry is not controlled, so it's a mixture. And it tells you what your product is. Again, Markovnikov's, where your hydrogens added to the side of the hydrogens, your nucleophile adds to the more substituted side. Okay, so make sure you go through and add these notes into your reaction table, and you should be able to start really doing a lot of work with this synthesis. All right, thank you very much, and I will see you in school.